some of the definitions of sets and ideas protruding from that. And in this session, we're going to start with discussions on operations on sets, and that is what most of the session is going to be about, just everything relating to operations on sets. All right. So when I talk about operations, there are 4 basic operations that we perform on a set: the union operation, the intersection operation, and the difference operation, and the complement operation. So let's see what each of these operations are. Yeah. Okay. So the union operation, the union of 2 sets would give us, as a result, a set that has as elements that belong to any one of the sets. All right. As long as the element belongs to any one of the sets, it will be there in the resulting union of the 2 sets. For example, here you have these 2 sets, 1, 3, 5. One set that contains the elements 1, 3, 5, and the other one that contains 1, 2, 3. The union of these 2 sets would have all the elements of both of these sets combined. Yeah. That is, as long as the element is present in any one of the sets, it will be there in the union. As you can see here, we have 1, 2, 3, 5 here. 2 is not there in the first set. It is still there in the union. 5 is not there in the second set. It's still there in the union. Right? So as long as it's at least in one of the sets, it will be there in the union. Okay. So we also see that we have 1, 3 in the first set, which is here. Then again 1, 3 in the second set. Why don't we have 1, 3? Well, why do we have 1, 3 only once in the resulting set? Is this correct? You see the elements 1, 3, they are there in both of the sets. Should we have something like this? Or is this correct? Just having 1, 3 once?
Yes.
Yes, ma'am.
Yes, ma'am.
Okay, why do you say so? Why do you think this is
We
correct?
can take on a one element from both the sets. We just learned it last class.
That duplications are not counted in sets, yeah?
Yes, miss.
Yeah, exactly. You're correct. So, yeah, and in general terms, for any set A and any set B, the union of these 2 sets, A union B, is defined in terms of set builder notations in this way. That is, for all elements X which belong to this set, the union set, X should belong to A, or X will belong to B. So you see, the union set has a similarity with the OR operation from the propositional logic. All right. Because in case of OR, if you remember, as long as at least one of the conditions are satisfied, you're good to go. All right. So the union has a similar idea, right? So here, that is how we would define it. For any element X that belongs to this set, that element has to belong to at least one of the sets in order to be in the final set. So if X belongs to A or X belongs to B, if this condition is satisfied, it will be there in the A union B set. Okay. Intersection. In case of intersection, we draw the parallel in terms of propositional logic with the AND operation instead. Why the AND operation? Because in case of intersection, what happens is that in the resulting set of the intersection operation, we will take only and only those elements which are there in both of the sets, right? That's why you have the AND operation here. All elements X which belong to the intersection set are such that X should belong to A and X should belong to B. That is, S must belong to both of these sets, right? As you can see here in the example, for the same sets in the intersection, the result of the intersection, you have only those elements that are there in both of the sets, the common elements that are there, right? So now for difference. When we talk about difference between 2 sets, first of all, here order is important. Unlike the previous 2 examples, order is important. Which one you put first decides somewhat what the result is going to be. Say, for example, here you have A minus B. In the resulting set, you would have all elements of A which do not belong to B. Okay, so if you have 2 sets A, B, and you want to find the difference in terms of A minus B, then all elements X which belong to the different set would be such that X belongs to A and X does not belong to B. Okay, both conditions have to be satisfied. X has to belong to A and X does not belong to B. Okay, that is, all the elements of A all elements of A. We want all elements of A that are not there in B. Okay. So here, as you can see, 1, 3, 5, the same example, the set that contains 1, 3, 5 minus the set that contains 1, 2, 3. Here, what do we have in the resulting set? We will take all elements of the first set, which are not there in the second set. So let's go by each element of the first set. The first one, 1. Is that there in the second set? Yes. So we will exclude that. 3. Then next we have 3. Is that there in the second set? Yes. So we'll exclude that one as well. Finally, we have 5. Is that there in the second set? It's not there in the second set. So 5 will be there in the resulting set. All elements of the first set that are not there in the second set. Yeah.
Miss, but if
Now,
we talk
what if
about
I change the
differences,
position? Yeah.
Miss, if you talk about differences, then we should also include 2, right? Like difference between A minus B.
Yeah. If you go by definition of, like if you go by what we know about how to calculate difference, you could think of it in that way, or the meaning of the term difference for that matter.
Yes,
The
miss.
meaning of the term difference, yeah, you could go that way. But in terms of set theory, we have to define some boundaries, right? So if you did something like that, then what about the case where you want some result like this? So you see what you're saying there. If we define differences in that way, then what about a certain scenario where I actually want only the elements of the first set, but not the ones in the second one? And also, this definition of difference helps us define other more complicated concepts in set theory and others as well. So this way of defining the difference in set theory is actually more helpful for us down the line. So that is why we define it this way. What you're saying, yeah, by the traditional definition of the word difference, that is what should happen. But in terms of set theory, what we do is the set that comes first, we only take the elements from that set. We only take the elements from the first set as long as they do not belong to the second set. All right, not the other way around. We don't do
Okay,
that by
miss.
default. Okay, just so that it helps us in defining other things. You will see that this definition of a difference is used in defining just the next operation, in fact, for that matter. Yeah. Okay.
Miss.
All right. Can you guys tell me then, if I switch the position of these sets, if I put 1, 2, 3 first and 1, 3, 5 second, then what would be the result then?
2.
Exactly. That is, if you had B minus A, yeah, thanks. So if we had B minus A, in that case, the definition would change to say that all element X would belong to the set B minus A such that X belongs to B and X does not belong to A. So yeah, based on where you place your sets, based on that, your result changes as well. Okay. Now finally, the complement operation. So for the complement operation, we have the complement of any set. You'll have a certain set, let's call it A. You have any given set A. The complement of this set is denoted by A bar in this manner, a bar on top of A. Or you can use the prime notation as well, like one of the students pointed out. Yeah, you're allowed. It's not mentioned here because oftentimes it's seen that in handwritten results, the prime notation sometimes is not readable. That's why we haven't included in the lecture slides. But yeah, you are allowed to use it. It's very much allowed to use the prime notation instead of the bar. Yeah. So yeah, anyway, the complement of set A is denoted in this way, A bar. And the way we define it, how we define it is that the complement of this set will have all elements that belong to this set as well, U minus A, where U is the universal set. Okay, so whenever we define a set, we define it in terms of the universal set as well. If the universal set is defined, then you have the definition with respect to which you have the set. Or if it's not defined, it's assumed by default that the universal set is a set that contains all objects. Okay. Usually what you will have is when a certain set is defined, you will also get an idea about what the universal set of that set is. That is which universal set this set comes from. Okay. If not, then the universal set is assumed to be the set of all objects. Okay. Now, since we know the value of universal set always by default, in that case, the complement of A right? The set A would be the set that contains all elements of the universal set the way it is defined, all elements of the universal set except for the elements that belong to the set A. Okay, that is, in terms of the set builder notation, the elements X which belong to the complement of A must satisfy this condition that X does not belong to A. All elements which do not belong to A, all elements which do not belong to set A will be there in the complement. All elements that do not belong to the set A will be there in the complement of A. All right. So X such that X is present in U, which is assumed by default, and X does not belong to A. Okay. So you see here as well, we use the idea of a difference. The way we define it in set theory, we use that idea here. Okay. So you exclude all the elements of A from where? From the elements of the universal set, but you don't go the other way around. No.
Ma'am, what is the difference between the complement and the difference then?
In case of difference, you can find out the difference between any two sets. All right. A can be any arbitrary set, B can be any arbitrary set. In case of complement, you're finding out the complement of any one specific set, and the complement gives you all the elements that does not belong to that set. Here you see A minus B gives us what? A minus B gives us all elements of A which do not belong to B. Here you take all elements which do not belong to A at all. All right. A kind of difference is with respect to some other arbitrary set. Both of these two sets can have any value. However, here, if you're talking about the difference, U minus A kotha jodi bole thako, all right, what does this mean? It means that you just exclude all the elements of A from the universal set. Okay. Here, A bar jagay jodi B bar thakto, B bar hoche U minus B hoto. C bar hole C equals to U minus C hoto. All right. The U is fixed. The U remains the same. Here, A minus B er moddhe A ekta arbitrary set, B o ekta arbitrary set. A can be anything, B can be anything. Okay. And here you always have the universal set. And the second set is assumed to be a part of the universal set by default. Yeah. So whenever you define a set, when it comes to the complement, you define it in terms of the universal set. So you already have the universal set, and the complement of any set would give you a set consisting of all elements that do not belong to set and only belong to the universal set, but not to that set. Yeah. So in case of A minus B, A can be any set, B can be any set. Yeah. And then you would have to find the difference between the two. In case of the complement, however, it's just U minus A. All right. U minus any set A. A is the arbitrary set, and U is a set that contains all objects, or if it's defined to be to have a little more restriction than based on that definition, you have to compute U. But by default, A belongs to U. All right. In any given scenario, all sets, kono ekta example A, all the sets that you define, by default, all those sets belong to you. If they do not belong to you, then it's not the universal set. Remember, the universal set contains all objects defined in a certain scenario. The universal set is the set of all objects in the universe. So if you go over a certain scenario or something where you have a number of sets, the universal set would by default have all the elements that are there in all the other sets. Yeah. So yeah, definitely there is a difference between A minus B and A bar. In A bar, you simply take all the elements that are not there in A. In case of A bar, the complement of A, you simply take all the elements that are just not there in A. In case of A minus B, you take all the elements of A that are not there in B. Very different definitions. Yeah.
Ma'am, can we write A minus B as A intersection complement of B?
Yeah. You could say that. Yeah. A intersection complement of B. Yeah, you could say that. It's the same thing. Okay, so here, let's look at an example of a complement. Let's say the set A contains all positive integers greater than 5. So the elements of the set that you would have, the elements that you would have in the set A would be 6, 7, 8, 9, and so on until infinite. All positive integers greater than 5. And the universal set is assumed to be the set of all positive integers. The set of all positive integers is the universal set. And the set A is the set of all positive integers greater than 5. That is 6, 7, 8, 9, 10, and so on. So if you were asked to compute the complement of A, how would you do that? You would have to get rid of all the elements of A. You would have to exclude all the elements of A from the universal set. All elements that do not belong to A will be there in the complement. Yeah. So what did we have in A? First of all, inside the set A, what are the elements that we had? 6, 7, 8, 9, 10, 11, and so on until infinite. So A সবগুলো element, we have to get rid of them from the universal set. And now, if you get rid of all those numbers from the set of all positive integers, which is our universal set here, then what are the numbers you're left with? 1, 2, 3, 4, 5. The set of positive integers, all positive integers key, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on until infinite. And in মধ্যে আছে 6, 7, 8, 9, 10, so on until infinite. So in A bar, the elements that we are left with is 1, 2, 3, 4, 5. Okay? All the elements that do not belong to A. Now, what if I define the universal set to be the set of all integers? Can any of you tell me, would we still have the same set here for A bar? If the universal set were the set of all
We would have
integers.
negative integers as well.
Exactly, very good.
Means there will be negative integers like to infinity.
Yeah. No, not to infinity. I mean, like in the, the negative integers would start from infinity, but the limit on the positive end would be until
Yes, yes.
5. Here it
Okay,
would be the
yes.
same, but before 1, we would have something like, let's say, dot, 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 minus 3, minus 2, minus 1, then 0, then 1, and so on, right?
Yes, miss.
Okay, what is the universal set where the set of non-negative integers? What is the universal set where the set of all non-negative integers?
Minus
We'll
1 to
have
minus
0.
infinity.
0, 0, 1, 2, 3, 4, 5.
Yes, we would have 0, 1, 2, 3, 4, 5. What is the set of all non-negative integers? Non-negative integers mean non-negative integers means
Oh, positive.
all
Sorry.
integers, all non-negative integers. No, not positive.
Including zero. Including zero.
Yeah, non-negative includes 0. So here in the result, we would just have a 0 here. Okay. All right then. Yeah. So, okay. A couple of interesting observations from the last session. So what if we brought in the null set here in these union intersection difference where we have 2 arbitrary sets involved? What if you were trying to find the union of a certain set with the null set? What if you were trying to apply the intersection operation on a certain set and the null set? What if you were trying to find the difference between a certain set, any arbitrary given set, or a null and a null set? How would they change? Let's talk about the difference first. Instead of A minus B, if we did A minus null set, what do you guys think would the result be? A minus null is going to be null. Okay, that's one possibility. What about the other guys?
1, 3, 5 money A. A minus null is
So
equal
now
to A.
that's A. Okay, so what about the rest of you guys?
Yeah, I think it's A as well.
Same, man.
Yeah, the majority is correct. It is going to be A. A minus null. The difference in the difference set in terms of that, A minus null is going to be A. Why is that? Because null is what? The empty set. And look at the definition. All elements that belong to the first set and do not belong to the second set. The elements of the first set do not belong to the second set. Why? Because the second set is null set in this case, and the null set does not have any elements at all. So we can say that, because it's safe to say that the resulting set, if you say that it's A, it does not belong to the null set because the null set doesn't have anything at all. So yeah, A minus null, the resulting set would have the elements of A, all the elements of A. Okay, A minus null will be equal to A. What if I change the position? That is, switch the position. Null minus A, if I did something like that. The null set minus A. What if we try to find out the difference in that way?
Means then
Then
it will
be
be
null. Yes, then it
Yes.
will be null. Because The first set is the empty set, and you need all elements from the first set that do not belong to the second set. You don't even have to go to the second part. All right. All elements in the first set. What do we have in the first set? Nothing. So null. All right. What about the intersection? What if I try to find the intersection between the null set and some other set? Let's say A intersection null.
Null.
Null, I guess.
Null, exactly. We need to have the common elements, yeah? So the common elements are none because the null set has nothing, so there is nothing in common. If we change to the position, would it affect the result for intersection and union?
No, for intersection,
No.
it will be null.
It would still be null, yeah? So in case of intersection, first of all, the intersection between any given set with the null set would give you null. And wherever you place the null set, in the first position or the second position, it would still be null. And in case of union, what you have is that come again?
Miss, if A union null, then we'll have A.
Yeah.
I mean,
Yeah.
union and difference will basically be the same.
Not really. I mean, like, depends on the position, yeah? Because in case of difference,
Yes.
A
miss.
minus null would give you A, all right? But null minus A would give you null. So if you change the position, the result changes as well. However, in case of union, A union null will be equal to A, just like you pointed out. But if you change the position, null union A, it would still be the same result, A. That is, any set union with the null set would result into the arbitrary set, all right? In case of union, wherever you place it. But in case of difference, where you place the null set is important, in the first position or the second position, in order to determine the result, yeah? So everybody clear on these ideas?
Yes. Miss.
Okay. So here we have a set of set identities. So yeah, these are very similar to what you had in propositional logic and what you knew there as the known equivalences. Remember the laws of Boolean algebra or the known equivalences that we had in propositional logic. These are nearly the same, except for the implication, I think. Yeah. So other than that, it's pretty much the same. Okay. So like if you know the rules there in propositional logic, that is if you know about the known equivalences, if you remember those, then they're the same as the set identities. It'd be very easy for you to identify the set identities as well. Okay.
Miss.
All right. Let me try and fire up that for you so that you can see that you can draw the parallel between the known equivalences and set identities.
Ma'am,
Yeah, we check. Yeah. Was there a question? Yeah.
is 0 both a real number and a non-negative number, right?
Yeah. Of course. Yeah.
Okay, ma'am. I was confused about it.
Miss, can you tell me about this De Morgan's law? I don't understand. What does this is complement of A intersect B, like the whole?
All right. For some reason, I can't really load the slide here. Okay. Let me just try and open it up in a new tab. Yeah. Okay. So De Morgan's law. Again, this is just the same that you had in propositional logic as well. So the De Morgan law says that if you have, let's look at the one in propositional logic. Hopefully, when we draw the parallel there, it'll be very clear to you. Okay. Okay. So yeah, here remember this one here in known equivalences. When you have a negation on a compound proposition like this one, how do you apply the negation? Remember, what do we first do? We first distribute the negation among the variables, yeah? And then the operator that's there, we just put the inverse one, all right? The opposite operator there, all right? If we have or, it turns into and. If it's on and, it turns into or, yeah? So that is the De Morgan's law. The negation on the compound proposition P or Q would give you not P, that is negation of P and negation of Q. So you first distribute the negation operator among the variables, and then if you have or, you convert it to and. Similarly, here you see the negation of P and Q. What do you get from there? First, you distribute the negation among the variables, and then since we had and here originally inside the parentheses, after applying the negation, and turns into an or. Do you remember this?
Yes, miss.
Okay. It's exactly the same thing here in sets. So the rules that you see here, the equivalences, the known equivalences here, these ones, this one, and these ones, throughout these 3 slides, the ones that you have here, you'll see them in set identities as well. Instead of the propositional variables, what you will see in set identities are variables which represent the set. Here you have the propositional variables, yeah, and in set identities, you'd have variables representing the sets. Here you have the logical operators. In set identities, you'd have set operations, yeah. The OR operator here becomes the union operation there. The AND operator here becomes the intersection operation there. And the negation operator here becomes the complement operation there. Yeah. So you see, very easy to draw the parallel. They're the same things. So here, for example, the De Morgan's law that you were talking about, what do we have here? The complement of the set A intersection B is equivalent to the complement of A union the complement of B. Right? That is A intersection B whole bar is equal to A bar union B bar. Isn't that the same as what we saw here in De Morgan's law, the first one, this one that you saw? Isn't that the same as this one? Think
Yes,
about
miss.
it. Yeah. So when you have something like this, the complement of A intersection B is it's equivalent to first finding the complement of A and then the complement of B and then finding the union between the two. All right. And same goes the other way around as well. If it's a complement of A union B, then you change the union to an intersection and distribute the complement to each of the variables representing the sets. All right. So here, all of these laws, you've already seen them previously. For example, the complementation law, this one, that the complement of A will give you A. This is something that you saw in propositional logic as well, in terms of the double negation law. Remember the double negation law? Negation of a propositional variable gives you what? The propositional variable itself in the normal form. It's the same thing. Okay? So all of these laws that you have, if you just understand, if you understood the known equivalences, then you understand these laws by default. Okay? So I'm not going to go over each of them. I'll give you some time to go over these in your free time and draw the parallel between these and the known equivalences. And if you have any question, you can ask me in the next question and or via email or in consultation, whatever. Yeah. Was there a question?
Ma'am, there is a complement law. There is A union null A equal to U. I mean universal set.
In the complement law, are you talking about the complement law here?
Yes, first one.
The first one, A union A bar is equal to U. Yeah. Yeah,
Yes,
that's
but in the previous slide, you said that A union A null is going to be A. No, not in this one.
no, but do you remember this law? P union not P. Sorry, P or not P. P or not P. Do you remember
ma'am.
that P or not P
Yes,
is
ma'am.
always
Yes,
going to be a tautology? Does that make sense? P or not P is always going to be a tautology. Or jehetu, since it's an or here, or har karone, P or not P will always be a tautology. If one is true, if one is false, the other one will be true by default. All right. If P is false, then not P will be true by default. If not P is false, then P will be true by default. So this will always be true. Okay. It's the same thing there in set identity as well. Now let's talk about what you were saying. So A union A bar is equal to U. So you were saying here, what were you talking about? When I said that
First one, union part.
yeah, union, yeah. So what's that? What was your confusion? Could you go over it again, please?
Ma'am, that time you said that A union A null will going to be A.
A union null set, all right? The null set and
Yes, ma'am.
the complement is not the same thing, okay? A union null set. A union with the empty set would be equivalent to A. Because why? Because in case of union, we will have we will have the elements in the resulting set from based on the elements that belong to at least one of the set. For example, A union B, এখানে a result কি থাকবে? The elements that belong to at least one of the sets. So A union null set এর ক্ষেত্রে চিন্তা করে দেখো, what is the result? It's still the same. Union এর definition তো change হয় না, it's still the same. All the elements that belong to at least one of the set, at least one of the set. Now, null set এর ভিতরে তো কোনো এলিমেন্টই নাই, right? Null set এ তো কোনো এলিমেন্ট নাই. So at least one of the set বলতে কি? A তে যে এলিমেন্ট আছে directly ওগুলো রেজাল্টে যাবে। null set এ তো কোনো এলিমেন্ট নাই। Here A union B তে we have 1 2 3 5, 1 3 5 A সেটে আছে আর 2 সেকেন্ড সেটে এক্সট্রা আছে, ওটা আবার আসলো। বাট সেকেন্ড সেটটা যদি না সেট হতো তাহলে তো সেকেন্ড সেট কোনো কিছু অ্যাডই করতে পারতো না, জাস্ট ডিরেক্টলি ফার্স্ট সেটে যেটা আছে ওটা ডিরেক্টলি রেজাল্টে যেত, রাইট? Does that
Yes,
make
ma'am.
sense?
Yes, ma'am. Yes.
Okay. Now, null set, which is the empty set, is not equivalent to A bar. Okay? The complement of the set A will contain all elements which do not belong to A. All right? All elements which do not belong to A will be there in the complement of A. Null set is what? Null set is a set which does not have any element at all. But can you say that for the complement of A always? Can you say that by default complement of A the kichu thakbe na? No, they're not equivalent. Complement of A will have those elements which do not belong to A. All the elements from the universal set which do not belong to A will be in the complement of A. Yeah? So they're not equivalent. So when we say A union A bar, it's not the same thing as saying A union null. All right? A union A bar will obviously be equal to the universal set. Why is that? Because in A, you have the elements of A, fine. And in A bar, you have all the other elements of the universal set that are not there in A, right? By definition, if you look at this. এর মধ্যে কোন এলিমেন্ট গুলো আছে যেগুলো তুমি বাই ডিফল্ট মানে এর মধ্যে যে এলিমেন্ট গুলো রাখলা ওগুলো আছে, এন্ড A বারে কি আছে? A bar complement of A এর মধ্যে আছে all those other elements from the universal set which are not there in A. দোনোটাকে অ্যাড করলে আর দোনোটাকে ইউনিয়ন করলে তো ultimately you get the universal set, right?
Yes, ma'am.
Okay, so any more confusion?
No, ma'am. It's clear.
Ma'am, can you explain the second one from the identity loss?
The second one as in the second complement law, or how we get universal set from A union A bar?
No. The second one from the identity loss.
Identity laws. Okay, all right, identity. The second one, A union the null set is equal to A. Yeah. Well, again, here, when you form the union, when you try to form the union set between two sets, what do you have in the resulting union set? All the elements that are there in at least one of the sets, right? So donota set এর সবগুলা element কে resulting set এ রাখতে হবে. All the elements that are there in both sets are going to be no. I shouldn't define it that way to avoid confusion. Any element that is there in any one of the sets is going to be in the resulting set, right? Eta ki, is that clear?
Yes, ma'am.
Okay. So if you look at this example, that's why 2 is there in the resulting set. 1 3 5 আছে, okay, from the first set, and then we see that 2 একটা extra element যেটা second set এ আছে ওটাও এখানে আসলো। Why? Because by definition, as long as they belong to at least one of the set, it will be there in the resulting set. See, or that's why. Okay. Now, instead of B here, instead of this set here, if you had the null set, তাহলে কি হতো? একটা empty set থাকতো, all right? You'd have an empty set here.
Yes, ma'am.
Okay. Okay, my computer is being unnaturally so slow right now. Okay. All right then. Okay. So here, what if instead of this, you had something like this? What would you have then? Think about it. Now, in union, you take all the elements that belong to at least one of the sets. এখানে at least one এর মধ্যে দুটো সেটের মধ্যে একটা সেটে তো কিছু নাই. The second set does not contain anything at all. So that set by default, মানে it will not affect the result at all. When you think about the union of these two sets, yeah? Because in the resulting set, you would have all the elements that are there in both sets, yeah? Sorry, in any one, at least one of the sets. All the elements that are there in at least one of the sets. Either a প্রথম সেটটাতে আছে or a second সেটটাতে আছে, yeah? Now the second set, as we can see, is empty. So what is there in the second set will not affect the result, because second set is simply there is nothing at all. So by default, in the result, what will you have? All the elements from the first set, yeah? So you'd have 1, 3, and 5 here. Does this make sense?
Yes, miss.
Okay, so you see, by default, whenever you have any arbitrary set and its union with a null set, the result will be the arbitrary set itself. Because union mane ki? Union mane hocche giye, in the resulting set, you will have all the elements that belong to at least one of the set. A empty set or null set e to kichu nai. Alright, so otar theke kono kichu to ashbei na. So by default, the result will be all the elements that belong to the first set, A. Okay? And if you did the same thing for intersection, that is A intersection null set jodi korta, in that case, you need to intersection a definition ki. By definition of intersection, the resulting set would have those elements which are there in both of the sets. Both. Donotate thakte hobe. That is the condition. In case of union, je kono ektate thakle hoy. In case of intersection, they have to be in both the sets. Okay? Now, if they have to be in both the sets, the second set is the null set. The null set is empty, right? So by default, you don't have any elements that are going to be in both sets, because null set is the kono element nei. And in order to have the element in the intersection set, ওই element, যে element intersection set বা result এ থাকবে, ওই element-টা এই দোনোটা সেটে থাকতে হবে। So এতে যে element গুলো আছে, will they ever be in the null set? No, because the null set is empty. Null set এ কোনো element-ই নাই। So এতে যে element গুলো আছে, ওগুলো null set-এ, they will never be there. So the moment you bring in a null set in an intersection, the result becomes the null set. The moment you bring in the null set in a union, the result is the other set by default. Okay? Does it make sense now, or is it still a bit confusing?
It's all clear now, miss.
Okay, all right, cool. Okay, so just, this is again very similar to a or false and a and false, I think, that you p instead of a you'd have p, but yeah. Okay, so if you went over the slides for propositional logic, you would see that there is one of the known equivalents talks about p or false and p and false, yeah? So it's very, very similar to that idea. What you have there, it's the same thing here, all right? So yeah, I'll go over the set identities later on your own, maybe. And if you have any question, ask them in the next session, all right? Which is going to be tomorrow. Okay, so yeah. So why we need set identities is because often we'll have to prove set equalities, all right? You'd have two combinations of sets in two sites maybe, and you'd have to prove that the two are equal, okay? So you can either do that using rules of logic, that is the known equivalences that you know about from propositional logic, all the rules of logic that we studied in propositional logic. By applying those, we will show set equality, okay? Here in this example, we will do this for one of the set identities themselves. Here, we will actually prove the De Morgan's law, this one, the first De Morgan's law. We'll prove this one here using the rules of logic. And similarly, you might be asked to prove a set equality for any combination of sets, all right? For any combination of set, you might be asked to prove the set equality using the rules of logic. So let's see how it's done. Okay. So this is the set, okay? Now let's see what it gets to. So this is the complement set of the A intersection B set, yeah? This is the complement of A intersection B set, yeah? So if we want to represent it or define it in terms of set builder notation, we want to define it using set builder notation, how would we do that? So all elements X which belong to this set, the complement of A intersection B, all element X which belong to this set should not belong to the set A intersection B, yeah? If you remember, definition of complement. Okay, so if you remember the definition of complement, the definition of the complement set, what was that? A bar, the complement of A, will contain all elements which do not belong to A, right? How did we define the complement of A? Simply, all elements X which belong to the complement will not belong to A, right? That's how we define. Just that. So if you want to define this set in set builder notation, this set would contain all elements X such that X does not belong to A and B. Sorry, A intersection B. Yeah? With me so far, you guys? This is just by definition of the complement.
Yes, ma'am.
Yes. Yes.
Okay. Now next, what can we say about this statement? X does not belong to A intersection B. X does not belong to the set A intersection B. What can we say about that? Isn't it the same as saying that you apply the negation on the statement X belongs to A intersection B? That is the opposite of the statement X belongs to A intersection B. The negation of this statement, it's the same thing, right? Can't you say something like that, that X belongs to A intersection B? The negation of this statement will be X does not belong to A intersection B. Yeah?
Yes, sir.
Okay. So if this makes sense, then next, what can we say about this statement? What can we say about this statement? First of all, when we say that X belongs to A intersection B, what does that mean? Let's see. X belongs to A intersection B. It means what? That X belongs to that X must belong to A, and X must belong to B, right? The AND operation here, because intersection by default, by definition, intersection means what? All the elements that belong to both sets. So X must belong to A and X must belong to B. So the AND operator here. So if based on that definition, if you do it here, X belongs to A intersection B. About this statement inside the parenthesis, can't we say this? X belongs to A and X belongs to B. Just by definition of intersection. Yeah. Next, what we will do is we will apply De Morgan's law as we know it from the rules of logic. In propositional logic, if you remember, in De Morgan's law, we saw that the negation on a compound proposition, how did we apply it? First, we distributed the negation among the variables, right?
Yes, ma'am.
And then what did we do?
Then change the operator.
Exactly, we changed the operator. First, we distributed the negation among the operands, and then we changed the operator. Yeah. This is what we will do here as well. We will first distribute the negation among X belongs to N and X belongs to B, and then we have AND in the middle that will change into an OR. Okay. So just the De Morgan's law in terms of propositional logic, or known equivalences that we already know of from the previous sessions of Unit 1. Yeah. Okay. Now this part, what is this statement? This statement is claiming that X belongs to A, right? However, we have a negation on top of it. X belongs to A. What will be the negation of this statement? The opposite of this statement. X belongs to A. What will be the negation of this statement?
X doesn't belong.
X not belongs to A.
X does not belong to A. Exactly. And the same goes for B. All right. So we can say something like this. Now, what do we have? X does not belong to A. And here we have X does not belong to B. Okay. Remember from the definition of complement, the complement of A stands for what? The complement of A means what? All the elements that will belong to this complement does not belong to A. And vice versa. If you had something like this as well, X does not belong to A. If you had something like this, X does not belong to it. It is talking about all the elements which belong to the complement of the set. Yeah? Vice versa. You can go in either direction. So here you have X does not belong to A. X does not belong to A, we can say that X belongs to A bar. If X does not belong to A, we can say that X belongs to the complement of A. Same goes for B. If X does not belong to B, we can say that X belongs to the complement of B. So far, does it make sense, everybody?
Yes, ma'am.
Yes, ma'am.
Yes,
Okay.
ma'am.
All right, then. Now, what do we have? X belongs to A bar or X belongs to B bar. Again, let's go back to the definitions. See, in terms of union, the union of two sets gives us what? Gives us a set where as elements we have those which belong to one set or the other one, all right? X such that X belongs to A or X belongs to B, and vice versa. Again, if you say that you have a certain element which belongs to A or belongs to B, you can say that that element belongs to A union B. Yeah, if you have a certain element X that belongs to A or it belongs to B, it belongs to A union B as well, right?
Yes, ma'am.
Yes, miss.
Based on the definition of union. So that's why what we have here, this one, we can interpret it in this way, that X belongs to A bar or X belongs to B bar. So X will also belong to A bar union B bar. If X belongs to this one or X belongs to this one, X will also belong to the union of these two sets. Yeah. So far, does it make sense, guys?
Miss, I have a question on the second line.
Yeah. The second line. This one?
Yeah, this one. You took negation and then like X belongs not belongs to became belongs to. What? Why did the intersection? Why did it not affect the intersection A intersection B?
It does in the later steps.
Because here we are talking about whether an element belongs to a certain set or not. Think about it. What does it say? It simply says that an element does not belong to this set. What is the opposite of this statement? The opposite is that the element belongs to this set. Yeah.
Yeah.
So if that's the opposite, then you have to bring the negation outside. What you're getting confused with, I think, is like negation in terms of the expression that an element belongs to a set, and negation in terms of De Morgan's law. All right.
Yes.
Here, when we apply De Morgan's law, okay, we're applying De Morgan's law here because we have an operand here. This is a compound situation. Yeah, we have an operator here. We have an operator here. We have an AND operation here that is going to be performed between two statements. One statement says X belongs to A, another statement says X belongs to B, and then we have the AND operator in between. So then, if you apply the negation on these things, then you have to apply the negation to each of them individually and invert the operator to get to the true result of the negation. However, here it's not like that. Belongs to is not a logical operator. All right, belongs to is not a logical operator. Belongs to is not a set operation. Yeah.
Okay.
Belongs to is a definition. Belongs to is a statement. Yeah, statement. Here you have an operator, and in terms of set as well, you would have an operation, a union operation or an intersection operation where you apply the De Morgan's law. Here, see De Morgan's law applied on union or intersection. But in the second line, we are not doing something like that. Belongs to is just a statement, or not belongs to is just a statement. The opposite of that, and the negation. Does that make sense?
Yeah, got it.
Okay. All right. So where were we? Okay. So we were here until here, where we established that X such that X belongs to A bar union B bar. Now, see what this means. We are defining this set using set builder notation, and we got here. It means that all elements that belong to this set, all elements X which belong to this set are such that those elements belong to the set A bar union B bar. So all elements X which are here in this set are also there in the set A bar union B bar. Yeah. All elements that are there in this set, intersection B whole bar. We are defining those elements here in this set builder notation, right? Equals to. So set builder notation, we started from there and we got until here. All of these are equivalent. It means that all elements X which are here in this set, in the original set, those elements are defined in this term, that all those elements also belong to this set, the A bar union B bar set. All right. So if the elements also belong to this set, can we not say that the two sets are equivalent?
Yes, ma'am.
Okay. Technically, if you think about technicality, you actually cannot say that. Here, see, so far we've had equivalences. We said that equals equals equals. However, instead of equals, actually actually it should have been implies. Yeah, here you'd get that, you'd get something like an implication, very similar to the idea of an implication. Because if you think about it, what we are claiming here is that all elements X which belong to this set are also there in this set. But are we claiming the opposite as well? I mean, that is all elements that are here also in the other set as well. So if you think about it technically, all you're saying is that elements that are there here in this set are there in this set. The elements that are here in this set exist in this set as well. But what if there are elements in this set that are not here? What if this set has some added elements, some more elements which are not here? All right. So technically, actually, you cannot straight away say that these two sets are equivalent to each other, because technically all you are saying is that all elements X which belong to this set also belong to this set. That's all you're saying. Yeah?
Yes.
So actually, in order to prove equalities like this, you'd have to go in the opposite direction as well. That is, right now, you proved that the elements that belong to this set also belong to this set. Now, if you did the thing in the opposite direction as well, that is, if you showed that, if you started with this, if you started with this definition, if you started with this set instead of this one, after this, if you started with this set and then showed, if you went on to show that the elements that belong to this set also belong to that set, then you have proved it in both directions. Something like a bidirectional implication being a tautology, something like that. The relation between an equivalence and a bidirectional being a tautology, something like that. So you've proved it in this way. If you prove it in the other way, it means that in both directions you can say that the elements belong to both sets. Yeah, and only then you can say that they're equivalent to each other. So what I mean to say by that is that what you did here, in order to prove that this set is equivalent to this set, you would have to do things in the opposite direction, do the same thing in the opposite direction as well. It's extremely obvious, I know, that if this can be done, you can do the same thing in the opposite direction. However, remember, we are dealing with the world of logic. We don't go with what's obvious or whatever. We have to show everything by logic. We have to address, even if there is some loophole, some technical loophole or whatever, even if there's the smallest loophole, we have to address that. Okay? So just doing something like this wouldn't be enough. This is more like an implication instead of an equality. I shouldn't actually use the equality here, because all you're saying is that the elements that are here are also in this set. But you also have to prove the thing in the opposite direction. That is, the elements that are here in this set are there in this set as well. That is, start from this set, and just like you did here, go ahead and show that the elements belong to this set as well. Is that clear to everybody?
So this will only be true when both of the sets have the same elements in them, right?
Yeah, exactly. So you proved it in one direction, you'd have to show it in the other direction as well, using rules of logic. Yeah? Okay, any questions?
No.
Okay. So now we'll talk about membership tables. So the idea of a membership table is very similar, very synonymous with the idea of a truth table. So in case of membership table, what we do is we represent sets in terms of whether an element is a member or not. So for a given set, if an element is a member of that set, if the element is in that set, then we represent it using 1. If the element is not in that set, if the element is not a member of the set, we represent it using 0. Okay? So very similar to the ideas of truth table, right? Very synonymous. So the reason we are addressing this is because just how you can prove logical equivalences using truth table, similarly you can prove that two sets are equal. So you can prove set equalities using membership tables. Okay, let me show you an example. See here, we have these two sets, these two combinations of sets. Yeah. So the first set is the combination of 3 sets A, B, C. The second one is also a combination of 3 sets A, B, C. Yeah. Now, the membership table. In the membership table, what we do is first we represent all possible combinations of the elements being in each of these sets. That is, all possible scenarios where the element is a member of one set and not the other, and all of that. So here you see how many variables do we have, both sides combined?
Three
Three
variables.
variables. Yeah, 3 variables representing 3 sets, right? So we have 3 sets in total. 3 sets in total, both sides combined. All right, 3 basic sets without applying any operation. Without applying any operation, basic variables representing sets. We have 3 of those. So for that, we would have again 2 to the power of 3, 8 combinations. Again, just like your truth table. In case of truth table, for n number of variables in the expression, you have 2 to the power of n combinations, right? You have the same thing in case of set as well. The number of sets you have in both sides of the expression, from there, you can find out the number of combinations that could be there. Now, what do these things mean? So the first combination stands for the scenario where an element is a member of A, a member of B, and a member of C, all of them. Why? Because for all of them, the value is what? 1. And 1 represents what? 1 represents the scenario where an element is a member of the set. So here we have 1 under A. It means that the element is a member of A. 1 under B, the element is a member of B. 1 under C, the element is a member of C. And then we go on to apply these possibilities into each of these expressions or each of these sets, and then see if the element is there in these sets or not. Now, if you think about it, throughout the membership table, if you see that the elements that are there in one set are also there in the other set, and the elements that are not there in one set are not there in the other set either. That is, you have the same elements belonging to both sets. In that case, you can say that they're equivalent to each other, right? That is the idea of the membership table. So, see, let's represent the expression on the left-hand side with S and the one on the right-hand side with T. Okay? So in that case, let's see what happens for the first combination. For the first one, we see that the element is in A, the element is in B, the element is in C. For this possibility, for this scenario, what happens for the set on the left-hand side and the right-hand side? That is what we will see. Okay. For the set on the left-hand side, again, parenthesis comes first. These rules still remain the same. The precedence, the laws of precedence that you had in logical equivalence, it's similar in set theory as well. So the parenthesis comes first. So inside the parenthesis, we have B union C. Now we will see, based on the first combination, will the element be in this set or not, B union C. Here, we have 1, 1. It means that the element is there in B and the element is also there in B. Now you guys tell me, if the element is there in both B and C, will it be there in the set B union C?
Yes, miss.
Yes, it will be. It's a union. As long as this element is at least one of the operands, it would be there. And we see that it's in both of them. So obviously, the element will be there in B union C. So that's one. Now that we know that the element is there in this set, now we need to see if the element is there in the intersection between this set and A. So we know that the element is in this set. But is that enough to find out if the element is in the intersection? No. Because in order to be in an intersection, the element has to be in both sets, right? So the element is in this set. We established that. Let's see if the element is in A. Is it in A? Yes, it is. It is in A. All right? So the element is in A and the element is in this set as well. So will the element be in the intersection?
Yes, miss.
Yes.
Is that clear to everybody?
Yes, miss.
Yes, ma'am.
Okay. So as you can see, the element is going to be in this set, the set S. Okay. Now let's look at T. Here for T, which operation will we go with first?
A intersect B and A intersect C.
Yeah. Yeah, the ones in the parentheses first, basically. So for A intersection B, let's see. Again, for the first combination, the element is there in A and the element is there in B as well. And for the intersection, the condition is what? It has to be in both sets. Is the element in both sets? Yeah, it is in both sets, as we can see from the combination. So the element is going to be in A intersection B. Similarly, is the element going to be in A intersection C? What do you guys think? Yes, it is going to be. So the element is going to be in this set and the element is also going to be in this set. So finally, we have the union. Is the element going to be in the union? It's in both sets.
Yes,
It
So it's
doesn't
obviously
matter actually. If
union.
the element is one of them, it is in the
Yeah,
in the
exactly. Yeah, exactly. And by that, you actually, the moment you found out that the element is going to be in this set, A intersection B, the moment you found out that, you didn't actually have to see even whether the element is going to be in A intersection C or not. This was completely unnecessary. The moment you found out, যখনই দেখেছো যে the element is going to be in A intersection B, by default you could have said that the element is going to be in the union, yeah? Because in order for the element to be in the union, as long as it's in at least one of the sets, it's good enough, right? If you saw that the element was not in this set, then you would have to see whether the element is in this set or not, in order to see whether the element is going to be in the union, right? So everybody gets the idea how to do these things?
Yes, ma'am.
Okay, so based on this, if we finally see that the elements that are there in set S are also there in set T, and if an element is not there in set S, it's not in set T either. If we can show that using the membership table, then we can say that these two sets are equivalent to each other. As you can see here, S and T have the same values, okay? If you wanted to break it down, you could do something like this, okay? The same thing. So here, instead of doing it in your head, what you could do is, for the set on the left-hand side, you did B union C first, right? So we have a dedicated column for B union C. B union C aage compute kore, we put it in this column. We find out whether an element belongs to B union C and put it here. And then we go on to perform the operation A intersection B union C. And similarly, for the right-hand side, we do these two things first, A intersection B first and A intersection C first, and have dedicated columns for those. And then it becomes easy to do the union just between these two, because we already know whether the elements belong to them. So see here, you don't have to remember what you did previously. You don't have to remember, okay, was the element in B and C? Was the element in A? You don't have to remember these things. So for starters, I would recommend going with something like this. That is, if you're just starting off, then for practice, you should start with something like this in order to avoid errors, yeah? Because if you break it down in this way, you don't have to remember much, and this has the maximum possibility of avoiding errors. So I would recommend starting with something like this, and then based on a lot of practice, you get to a certain point that you're comfortable with these ideas to that level that you can do this all in your head. Yeah? Was there a question?
Yes, Miss, I have a question.
Yeah, go ahead.
Miss, this S and T, we can say this is biconditional. Can we say this is biconditional because like, we can prove them from both sides? Like, this is not an implication.
It's a biconditional. That is a tautology. The biconditional, yeah. Biconditional, yeah. That is a tautology, yes.
Okay, Miss.
Not just a biconditional. A biconditional can have the truth value of true or false. Remember, the biconditional is true when both operands have the same values, only then. So you could say that if the biconditional between them is true, then they're equivalent to each other. You could say something like that, okay? Not just by default that it's a biconditional. It's not like that. Yeah, if the biconditional is true, in that case, I mean, it is what you said, just with an added detail that the biconditional has to be true, okay? The biconditional, if the biconditional between these two sets is true, that is, if one element, if an element is in one set, then it implies that it's the element is in the other set. And if an element is in the set on the right hand side, it also implies that the element is in the left hand side. If that is true in both directions, then you can say that they're equivalent to each other. Yeah.
Yes,
that is when we're trying to prove it using rules of logic. But in membership tables, just like truth table, it's a lot simpler than that. All right, the process. All you have to show is that for all possible scenarios where an element is a member of a certain set or not a member of a certain set, for all possible scenarios, the elements, if they're a member of one set, they're also a member of the other, and if they're not a member of one set, they're not the member of others, as you can see here. Doing that is enough, okay? So as you can see here. So for all possible combinations, B union C computed, A intersection B and B intersection C computed, and from that, the final expressions computed, and you see they have the same membership values. That is, the elements are members of the same sets or the same combinations, right?
Miss.
Yeah.
What if এখানে যদি একটার ভিতরে 1 থাকতো and the opposite one it has 0, then what would you have done?
That is, let's say for the first combination, let's say just for argument's sake, that প্রথমটাতে এখানে 0 আসছে, something like that.
Yes, miss.
In that case, they're not equivalent. In order for two sets to be equivalent, they have to have the same elements in them, yeah?
Yes, miss.
All possible combinations, they would have to have the elements in them in the same scenarios for the same possibilities. So for the same scenarios, দেখো এই প্রথম তিনটা সিনারিওতে এই যে ফার্স্টটাতে the element belongs to the first set. For the same three scenarios, the element must also belong to the second set, and vice versa. And the rest of them, baki scenario gulate, the element does not belong to the first set, and so it should not belong to the second set either, and vice versa. Otherwise, they're not equivalent to each other. Yeah? Is that
Yes,
clear? So any questions, guys? Any other questions? Okay, so let's move on to the idea of a generalized union and a generalized intersection. First, let's define this. What do we mean by a generalized union and a generalized intersection? So far we've looked at just two sets. You can have more than two sets, obviously. We've looked at union between two sets or intersection between two sets. You can have more than two sets. You can have unions between 3 sets or 4 sets. But what about any collection of sets? What about n number of sets? So you see, if you have n number of sets where n can be any arbitrary positive integer, if you have n number of sets and the union, if you want to compute the union between these sets, all of these n sets, এই পুরো n number of sets যে collection সবগুলোর মধ্যে আমি union operationটা perform করতে যাচ্ছি, then that is what we call a generalized union. Okay, a generalized union, like much like this one, where you perform the union operation between a number of sets, n number of sets, all right? A1, A2, A3, A4, A5, so on until n, an. You want to perform the union between all of these sets. So that is a generalized union. And this is how we represent it or symbolize it. You have a large U and then the range I is equal to 1 to n. What does I stand for? The index of the set, all right? You see, if based on the index of the set, you can say which set it is, all right? A1, A2, A3, A4, so on. So the union is for all sets AI where I is from 1 to n. For all sets AI where I is equal to 1 to n, you're trying to find the union. So this is how we represent it, all right? This is one way of representing it. This is another way of representing it. The union of all sets AI where I is present in some set I which holds all positive integers, all right? You wouldn't have to define the fact that it holds all positive integer. Just by using the symbols I and placing them in these specific positions, it's very clear, because based on the use of the symbol I and the position, we can tell that it's an index, and indexes are, in terms of discrete mathematics at the very least, the indexes are all positive integers. We use only positive integers for indexes, yeah? Or non-negative integers in some examples maybe, yeah? So it is by default assumed to be either positive or non-negative integer, yeah? Mostly positive integer, most cases. Unless otherwise defined, yeah? So the union of all sets AI such that I belongs to the set I, which is constituted of all positive integers, all possible indexes, basically. So yeah, if you define it using set builder notation, see that we're defining it using the existential quantifier. Here, this one here, what is this? This symbol, what is this? Guys, what is this? The
Existential quantifier.
This is the existential quantifier. We're using this existential quantifier to define the union operation. Why is that? So in this generalized union, we will have all elements X such that for at least one I belonging to I, X belongs to AI. That is, for at least one of the indexes in this range. For at least one of the indexes in this range, the set corresponding to that index contains the element. As long as that's true, it'll be in the union. That is, in simpler words, as long as the element is in any one of this set, as long as the element is in at least one, as long as the element is in at least one of these sets, it'll be in the generalized union. All right, that's why the existential quantifier, at least one I. Yeah, there can be more, yeah, but at least one. So based on the definition of union, we use the existential quantifier here to define it. Okay, does everybody get the idea of a generalized union? The idea of it. We'll see the application later on, but do you get the idea of the generalized union?
Can I
It's a
make
good idea, but the formula, the last one, I can understand it really. But I understand the idea that at least one has to be present in any set.
Which one did you not understand? Come again.
This last one is this
Last
last.
part. Okay.
Yes.
So here, what are we saying? For at least existential quantifier মানে কি? Existential quantifier পরে statement যেটা. For at least one I present in I, right? For at least one I that is in I. That is for at least one value of I in this range. এই পুরা রেঞ্জের মধ্যে at least একটা I এর জন্য X must belong to the set corresponding to that I. That is I to can start from 1 and go on until n, right? For at
Yes,
least
yes.
one of the values of I, the corresponding set that you get, at least one of those values of I, the corresponding set that you get, X must be there in that set in order to be in the union. That is what we mean when we say that X has to be in at least one of these sets, right? X has to be in at least one of these sets মানে কি? এই generic ভাবে যদি represent করি, X has to be in at least one of these sets মানে কি? It means that X has to be in at least one AI where I represents 1, 2, 3, 4, 5, 6, and so on until n, right?
Yes,
So,
miss.
X has to be in one AI where at least one for at least one I from the set of I, okay? For at least one of the indexes, basically for at least one I present in I মানে কি? For at least one of the indexes, X has to be present in the set corresponding to that index. That is what it means. It's exactly the same thing as saying that X has to be there in at least one of these sets. Each of the sets, their individuality is represented by what? By the index. The fact that these are different than each other is represented by what? The index, right?
Yes, miss.
So that's why we put the condition on the index. শুধুমাত্র ইন্ডেক্সের বেসিসে তো তুমি বুঝতেছো যে these sets are different than each other based on the value of I. So at least একটা ইন্ডেক্স, একটা স্পেসিফিক কোনো ইন্ডেক্সের জন্য যদি বলতে পারি যে ওই ইন্ডেক্সের ওই সেটের মধ্যে x আছে তাহলে এটা ইউনিয়নের মধ্যে থাকবে. That is what we are saying here. At least একটা index for at least one I present in I, X has to be present in AI. Now does it make a little bit more sense maybe?
Yes, miss.
Okay.
Thank you.
All right. Okay. Now generalized intersection. In case of generalized intersection, what would be the scenario? In case of generalized intersection, however, in order for the element to be in the generalized intersection, is it enough for the element to be in at least one of the sets?
No, miss. They have to be in all for all I.
Exactly. They'll have to be in all of the sets that are there in the generalized intersection. As a union জায়গায় যদি intersection থাকতো, the element would have to be in all of these sets. Union জায়গায়, if you had intersection, the element would have to be in all of these sets in order to be in that generalized intersection. Okay? So, in that case, the union symbol, the large union symbol, of course, also changes. Here, instead of this U, big U, you'd have a large version of the intersection. Here as well, you'd have intersection. And here, in this definition, will we have the same quantifier for intersection?
No, miss.
No.
Because
Why?
for
Because
all
we need all these sets to contain that element.
Yes, because here it says at least one I, at least একটা ইন্ডেক্সের জন্য ওই ইন্ডেক্সের corresponding সেটে x থাকলে ইউনিয়নে generalized ইউনিয়নে থাকবে, বাট ইন্টারসেকশনে তো at least one condition না, ইন্টারসেকশনে কন্ডিশন হচ্ছে কি সবগুলো ইন্ডেক্স, for all of the indexes x has to be present in AI, for all of the indexes. That is, by that we mean x has to be present in all of the sets, right? So there we cannot use the existential quantifier. Do you guys have any suggestion about what we will use instead of the existential quantifier then?
It's universal quantifier.
Yes, the universal quantifier. Yes, exactly. So instead of the existential quantifier, we will use the universal quantifier here. Because here we want to say that for all I, that is for all the indexes, x has to be present in AI. Yeah. Okay, any questions
Miss, can I
regarding?
ask another question?
Yeah,
This,
go ahead.
what is this uppercase I? What does that mean? It is a set that contains the index.
Yeah, it is a set of indexes. And
Okay.
the set of indexes is by default assumed to be all positive integers unless otherwise defined. Sometimes it can be all non-negative integers. Even in that case, it will be defined. All right.
Okay, miss. Thank you.
The range of I, that is, it will be defined. Okay, any other questions? All right then. So generalized unions and intersections defined here in terms of different ranges, as in 1 to n or 1 to infinity. In one case, A range A indexed range A. What are we saying? I is equal to 1 to n. 1 to an arbitrary but finite positive integer n. But here we are saying I is all positive integers. All positive integers. There's a difference because all positive integers goes on until infinity. Here we have a certain range. N represents any arbitrary positive integer but finite at the end of the day, right? But here this encompasses all positive integers because we have I is equal to 1 to infinite, I is equal to 1 to infinite. Okay. So in terms of these ranges, the unions and the intersections are defined here. So for the first one, you see x such that x is present in AI for at least one integer I within this range. Okay. So at least one. Why at least one, guys? Why are we using the term at least one?
Because of generalized union.
Union.
Because it's a union. Because it's a union, we are using at least one. This expression. X present in AI for at least one integer I. For at least one integer I in this range, that is in this range, 1 to n, in this range, for at least one integer I, if the element is present in the corresponding set in that index, then it will be in the union. But in case of the intersection, we have to use the term for every integer I within the same range, for the same range. In case of 1 to infinite, in that case, you can just simply say for at least one positive integer I. We don't have to define the range in this format, right? Because here you have to define the range because 1 until a finite positive integer, an arbitrary value, but the moment you specify the value of n, it's a finite range. However, here 1 to infinite mane ki? All positive integers. 1 to infinite mane to all positive integers, right? So here, x present in AI for at least one positive integer I. X present in AI for every positive integer I. All right. So any questions regarding these definitions of unions and intersection?
No, miss.
Okay. So we will do these two examples at the start of next class. All right. I don't want to push you any further. There's no way I'll be able to finish this example with the amount of time we have left anyway. So what I'll do is I'll end this recording here and you guys can go ahead and ask any question if you have any.